All right. Welcome, everyone. Thank you so much for joining us for the 2025 ISAR Virtuaeolian Seminar Series. The entire ISAR board is excited to continue this tradition with Dr. Chloe Daudon. Before I turn it over to Philippe to introduce our speaker, I'm just going to go over the structure of today's webinar. Please keep your microphones off unless you're called on in the Q&A section after the talk. Please feel free to type in questions at the chat at any time. We will wait till the end, though, to read those aloud. During the Q&A, you could also raise your hand if you, again, prefer to ask your question out loud. Hopefully you just heard, this meeting is being recorded and it will be shared with the ISAR community on our website. You can check out our past talks on our website as well. And please, we encourage you to hang out until the very end where we'll share some important updates, such as the ISAR awards, as my background is hopefully showing a little bit there. And lastly, most importantly, we ask everyone to contribute to creating and maintaining a welcoming and respectful environment that fosters diversity, inclusion, and belonging. And so now I'll turn it over to Philippe. Thank you.
Thank you, Maddie, and thank you, Chloe, for accepting to give this this talk for ISAR. We are very happy to welcome you on this webinar. So, just a few words of introduction. So, Chloe, you are at the moment a postdoctoral researcher at UC Santa Barbara, and you are interested by interactions between surface, atmosphere and surface on Earth and other planetary environments. You did your PhD in France, in Paris, at the IPGP, where you have studied rivers on Titan. And then during a first postdoc at Caltech, you've been interested by dune dynamics. Where you have focused on the interaction between flow and sand dunes, both on Earth and on Mars, and this is what you're going to present today. And so now, as I was saying, you are a postdoc in Santa Barbara and also working on dunes, but dunes on beach and associated with the sea level rise in California, but today it's more about what you did during your first postdoc. So we are very happy to listen to you.
Thank you. Thank you for having me. Thank you, Philippe, for the introduction. Where is it working? Yes. Okay. So yes, as you said, I will today present you the work I've been doing during my postdoc at Caltech. Where I was trying to link bedform migrations to wind speed. So during the first part of this talk, I will be showing how to link dune migration to wind speed on Earth. So it's possible that you've already been the first part of this talk because I have already been presenting this part, but the second part is on how to link dune and ripple migration on Mars to wind speed. This is quite new and it is ongoing work, so maybe you haven't seen, hopefully you haven't seen this work. Okay, so let's jump in and let's go to Earth and look at barchan dunes migration. So here you see barchans in Saudi Arabia. And so I am displaying a planet image time series of barchan dunes migrating, and at the same time I'm also displaying the wind velocity. And so you see that the peak in the wind velocity is associated with sand moving in the image. So this is in situ wind velocity in a nearby station. And I think this animation is a good example to prove that we can monitor eolian activity from space. And so during this talk, I will show you how to link the movement of those dunes to the wind velocity. Okay, so here you see that I'm displaying one image per day. But if you choose like the right time span in between two ortho images, you can actually measure the displacement of the dunes by doing our feature tracking, which is so when you have a first ortho image at the time t and another ortho image at the time t+1, you basically just measure the displacement of the dune, or you can also use image correlation. using like software, like for example, CosICore, etc. And so once you have the displacement of this dune, which is the dune migration rate, you just need to multiply it by the height of the dune at the crest to get the measured migration rate at the crest of the dune. So this is in the following of the talk, what I would call the sand flux that we measure from remote sensing. And you see that I will use this measure as a ground truth to compare it with sand flux that I'm trying to infer using wind speed. So to link the sand flux to the wind speed, so this can be actually very useful on Earth, because if we know how to do that, then it means that you can estimate the sand flux and the dune migration anywhere on Earth if we can use data coming from climatic model. And on Mars, it can also be very useful because it can work the other way around. So let's say that you know the displacement of the dune, then you could come back to the wind speed that was involved in the displacement of this dune. But so to do that, you need to have an eolian transport law. And so there are a lot of them in the literature. Here I am only displaying 3 of them, so that you see that they all depend on a lot of parameters, so the density, the gravity, the grain size, etc. And so all of these laws, they are based on several assumptions, which is first that the flow is saturated, uniform, and steady, which is, of course, not the case in the real world. We do have some spatial and temporal variation of the wind speed that we need to take into account. And also these laws, they have been established for a flat and a horizontal surface, but in the case of dune, we also need to take into account the spatial variation and the influence of the dune on the wind speed. Okay, so because of all these assumptions, we can wonder how the wind speed that is predicted using those transport laws compared to the one that we are measuring from remote sensing. And so I will try to answer this question using two applicative cases on Earth, one in Qatar and another one in Saudi Arabia, where I do have barchan dunes. So for both of those sites, I have wind data, so in situ wind data, and later I will also use climatic model data and specifically ERA-5 reanalysis data. So I know the grain size and I have ortho images and DEMs. And so the goal, as I said, is to compare the sand flux that is measured from remote sensing and the one that we predict using the transport law and the wind data. Okay, so as I said, those laws, they have been established for a flat and horizontal surface, but because I was measuring the sand flux at the crest of the dune, I need to have the wind speed at the crest of the dune. And so the wind data that we have from meteorological station, they are given for the surface that is flat, and it usually does not take into account the dunes. So if I want to have the wind speed at the crest of the dune, I need to add what's called the speed up effect, which is the influence of the topography of the dune on the wind speed. Because when the wind encounter an obstacle, it's going to be accelerated here up to the crest of the dune due to the compression of the streamline. And so this has been theorized in the 70s by Jackson and Hutt, who came up with this equation. So this is actually a simplified equation, just to make it simple. But basically it says that the velocity of the wind at the crest is equal to the velocity of the wind over a flat surface, multiplied by an amplification factor. And this amplification factor depends on h over L, which is the aspect ratio of the dune. So h is the height of the dune, and L is the length from the toe to the crest of the dune. The issue with this theory that it's only applicable for low hills, so when the aspect ratio is below 0.1. But in the case of our field of study, so in Qatar and Saudi, and also other dunes, barchan dunes on Earth, the H over L can be above 0.1. As you see here in this histogram, actually more than half of the dunes have their H over L be above 0.1. So we need to come up with another description of this speed-up effect for H over L above 0.1. And so for that, we used a computational fluid dynamics model, which are a model that can help understand how a fluid reacts to a given topography. So here in entry, I will give the DM of a barchan dune in Qatar that has been reconstructed using drone images. And so this is the output of the CFD. And so I have measured the amplification factor, which is the U star at the crest, so the shear velocity at the crest, divided by the shear velocity over the flat surface. And because I want to measure this amplification factor for different H over L, what I did is that I artificially varied the height of the dune while keeping the length constant, so that I have different H over L and I'm keeping the same geometry. So by doing that, then I can measure the amplification factor for different H over L, which are the points that you see here, and I have also varied the aerodynamic roughness. Then I can fit a law so that for any given H over L, I have the amplification factor. And so those different factors, like this A, B, and C, they actually vary with the aerodynamic roughness. And so if we compare to previous studies that have measured this amplification factor, we see that we have a pretty good agreement. And what's interesting is also to compare with the previous Jackson and Hunt theory. And so what's interesting here is that you see that we have a very good agreement up until like 0.12. So when H over L is below 0.12, we have a good agreement, but above 0.12, the Jackson and Hunt theory keeps increasing, while with our CFD measurement, the amplification factor is diminishing. And when you think about it, it actually makes sense that at some point, when your slope is increasing too much, that your amplification factor is diminishing. Okay, so then, so when you have a dune, you need to measure its aspect ratio so that you have its amplification factor at the crest, and then you just need to multiply the wind speed or the shear velocity to this amplification factor, and so that you will have the wind speed at the crest of the dune. Okay, so thanks to that, then I can compare the measured transport rates that I have measured from remote sensing at the crest of the dune to the model transport rate. So just again to summarize the model transport rate, I'm using the transport law, wind speed. So for now, I will use in situ wind speed and the amplification factor. And so ideally, both of those measurements, they should align along this one-to-one line. Okay, so the first thing that I did is that I have compared different transport law. And so here, every point corresponds to a dune in Qatar, and every triangle corresponds to a dune in Saudi. And the different colors corresponds to different transport laws. And so you see that this dark blue law here is the one that is closest to the one-to-one line. And so this is the transport law that I will be using for the rest of the presentation, which is the Kolkata transport law. So then I just have added some sensitivity to the parameters of the transport flow to see if we still have a good agreement between the model transport rate and the measured transport rate. And we actually still have a very good agreement between both. So for in-situ wind data, it's working very well. But then what I wanted to see if what's happening if I use wind data coming from climatic models. So particularly for this work, I will use ERA 5-land reanalysis data that have an hourly sampling. So here I was using a minute sampling, in situ wind data with minute sampling. And so the first thing that I did is that I looked what's happening if I'm using an hourly sampling instead of a minute sampling. Am I underestimating the sand flux too much or not? And so actually, if you compare the migration rate that you predict using an hourly sampling instead of a minute sampling, you are only underestimating the sand flux by 5%, which is very reassuring because those climatic data, they have an hourly sampling. So then I have compared the data, in situ wind data with an hourly sampling to the model data with an hourly sampling coming from ERA 5. And I see that if I'm using the model data instead of in situ data, I am also only underestimating the sand flux by 5%. So this model, this ERA 5 model, they are smoothing a little bit the data, but not too much, at least on those areas. Okay, so then I have used the ERA 5-land reanalysis data and compared the model migration rate to the measured migration rate. And we see that we have a pretty good agreement between both. We are always better than a factor 2. And so I was very happy with that. And so thanks to that, by using wind measurements, wind data coming from climatic model, I can estimate the sand flux of the dune. Okay, so in conclusion, I have shown you a workflow to link the wind speed to the dune migration on Earth. I have shown you also a new relationship for the speed-up effect. And I think we can say that the ERA 5-land can be used to predict sand flux on Earth, as we see that the predicted sand flux fits the measured sand flux pretty well, always better than a factor 2. And so this workflow is applicable on any other region on Earth and also on other body. And so this is actually the thing that I will do in the second part. I will try to use this workflow on Mars. On Mars, so you know what I said is that on Earth, this is very useful because you can use climatic model to infer the dune migration anywhere on Earth. And on Mars, I will use it the other way around. So I will use the migration of the dune to come back to the wind speed that was involved in the measurement, in the movement of those dunes. So here I'm making two assumptions. So I'm assuming that I can use the same workflow that was calibrated, established on Earth. And also I will say that I can approximate the wind speed distribution by a Weibull distribution. This assumption is commonly made on Earth, where we see that the wind speed distribution is usually very well described by a Weibull distribution. And a Weibull distribution can be characterized by two parameters, the scale parameter C and the shape parameter K. Those two parameters are independent. And so for this work, I will start by using barchan dunes in Nilipatera, which is in the northern hemisphere of Mars. And I will look at their migration over 1 Mars year using high-res images, which are 25 centimeter resolution. Okay, so what I know here for this work is the measured dune migration rate, because I can measure it using ortho images of high-res. and I have the workflow to compute the model migration rate. The only thing that I'm missing and that I want to find is the wind speed. And so I will approximate it by a Weibull distribution. So basically what I'm missing is the C and the K parameter. And so what I will assume also is that I will fix the parameter K and say that K is equal to 2, which is the same as saying that it's a Rayleigh distribution. And also this is something that is commonly assumed on Earth when you only know the average wind speed. And once I have found the C parameter, I can come back to the mean wind speed by using this equation. Okay, so let's start. So for example, if I take C is equal to 7.3, I see that my model migration rate is too low compared to the one that I'm measuring. If I'm using like C with 0.2 is equal to 2.8, I have my model migration rate are too high compared to the one that I'm measuring. But if I'm using C is equal to 5, we see that we have a good agreement between the model migration rate and the measured migration rate. So this is the wind speed distribution that I'm choosing. And so this is the mean wind speed distribution over 1 Mars year. And from this parameter C, I can come back to the mean wind speed, which is equal to 4.5 meter per second. So this is my mean wind speed over 1 Mars year in Nili-Patera. So here I have my mean wind speed and my wind speed distribution over 1 Mars year. But then what I want to do is to get the subannual variability of the wind speed. And for that, I cannot use the dunes migration because on Mars, because of the lower gravity and the lower density, the dunes are very big and they are very slow to move. So you see, for example, here, the measured migration rate is around 1 meter per year. But instead of using the dune, I will use the ripples migration, which are those features that you can see here moving. And they move much faster than the dunes. Like within a couple of months, you can see them moving from space. So they are 4 meter. So here I'm talking about the large ripple, which are 4 meter wavelengths. And so using those ripples, I can build a time series of correlation maps where I see the ripple migrating through time with a time span of a couple of months. And so, for example, here, when you look at this figure from Robach et al., where they are displaying the migration rate through time, it's pretty clear that you do have a seasonality of the ripple migration. So now I want to link this ripple migration to the wind speed. And to do that, I will use that method that rely on the idea that dunes have the same seasonality as ripples, meaning that the sun flux of the dune at the time t is equal to the mean sun flux of the dune multiplied by the seasonality. This seasonality, I can have it using the migration of the ripples. This mean sun flux, I can have it by measuring the migration of the dune. And this sun flux at the time t, I can have it using a transport law. So here, this is again the Coquetel transport law, where, and thanks to this transport law, I can isolate the U star, and I can then estimate this U star for every dune, at every time step where I do have a ripple migration measurements. So for every dune, and at every time step, I will invert this U star. And then from the U star, I can also get the wind speed by using the law of the wall. So this is how I get this figure. So every color here corresponds to a dune in Nili-Patera. And so thanks to that, I can get wind speed time series on Nili-Patera. So then I am averaging all those dunes by saying that the wind speed should be approximately the same for the whole dune field. And so I have my wind speed time series on Nili-Patera. So then, because I want to have sort of a validation of this method, I am also comparing this to a nearby site. So I will do the same method on a nearby site, which is Meroe Patera. This is 60 kilometers south of Nili Patera. It also there's also barchan dunes on this site. And also I will use the closest in situ wind data that we have, which is the March 2020 wind data. This is 200 kilometers north of Nili Patera. And so because it's a bit further away, I'm not saying that we should necessarily have exactly the same wind speed, but at least we should have the same seasonal pattern and this kind of the same variation. Okay, so this is Meroe Patera. I have done the same. So every color corresponds to a gene in Meroe Patera. I'm taking the average of those time series, and then I'm comparing it to Nili Patera. So what's interesting here is that we see that they both have kind of the same pattern in the sense that you see that the wind speed is diminishing, then it stays stable, and then it's increasing again. But the Meroe Patera looks shifted a bit. And I think that it could be due to the fact that those measurements, they were not done over the same year, because unfortunately I don't have the ortho image for the same year. And so this could just be due to the fact that these are different years. So it's possible that for 1 year, I don't know, the summer or the winter was longer. So this is one explanation. And so then I am comparing it to the March 2020 wind data. And so we see that we have a pretty good agreement. Even though it would be nicer to have a bigger data sets to compare for at least half 1 Mars year. But for now, I don't have those data. Okay, so the idea is that then if I have the wind speed time series, then at any time of the year, I could infer a distribution, a wind speed distribution. Again, assuming that k is equal to 2, then we could get a wind speed distribution any time of the year. Okay, so this is still a work in progress. So I'm planning on also adding some sensitivity to those time series. So I want to see how sensitive it is to the transport load that I'm using. And I will also try to vary the parameters that are within those transport laws, as well as the aerodynamic roughness. And I'm also planning to compare this to some GCM outputs of those regions. But so just to conclude on the work that I have been presented. So on Earth, I have shown you a workflow to predict dune migration using climatic models. And on Mars, I have tried to infer wind speed distribution from dune migration over 1 Mars year, like the average wind speed distribution that is average over 1 Mars year. But while I was using the ripple migration, I was also trying to infer a time series of the mean wind speed. Thank you for your attention, and I'm very happy to take any question.
Thank you, Chloe.
Thank you.
Feel free to type questions in the chat. Philippe and I can read them aloud, or if you'd like to raise your hand, you can unmute and ask Chloe directly. Lots of applause. I can start off with one while people think of their questions. Chloe, I've only recently used the ERR5 data, so I'm not super knowledgeable at it, but could you describe a little bit more when you were talking about you have higher resolution on Earth? I think it was like 1 minute or something at the minute scale,
Yes.
and comparing it to the hour.
Yeah.
Because could you talk about what the ERR5 like hour time step is?
Yes, so ERA A5, they will give you the wind data with an hourly sampling. It's the best that they can do. So actually, it's pretty good. It used to be 6 hour sampling, and now it's hourly. And so because of that, I was wondering, is an hourly sampling enough to predict the sand flux? So that's why I was just starting by comparing for my, so this was using the in situ wind data. So I just downgraded the sampling and compare what's happening if I'm using hourly instead of minutes. And so because you're smoothing the data, you start to lose gusts and everything. But it's very reassuring because I'm only underestimating the sand flux by 5%. And then I also compare to, so if I take the climatic model at this location, the prediction of the wind speed at this location, and compare it to what I actually have with my in situ data, because it's not just the sampling that can be off. I mean, just also the prediction sometimes can be smoothed or a bit off, but actually I was only so by using the model wind data, I was only underestimating the wind speed by 5% instead of the in situ wind data. Sorry, was that clear enough?
It was, I guess, when you say hourly sampling though, is it like the instantaneous at the top of the hour, or is ER5 actually like average or some kind of statistic over the hour?
Oh, that's a oh, I'm not sure. Yeah, okay. I see your point. I'm not sure.
That's okay. We can ask Varsha, would you like to unmute and ask your question or type it in the chat?
Hi, Chloe. It's Varsha here, and the presentation was very good. And I was having a small query related to the mass aspect of your study. So I was wondering, what is the time difference between the Mars 2020 data that you compared with the wind speeds in Marupatera? Like, is it in the same year that you compared?
No, yes, no, that's not the same year. It was later. It was another year actually. Yeah. But
Do you remember how different that was?
like because I have to remember what time of the which year I have used my ortho images on Nilipatera, and I don't remember. I don't know. I don't remember. I would say it's couple of
Okay.
years. Sure, I can check that. Yeah, but it was not the same year.
Okay. Yeah. And do have you checked whether there is any way, like maybe applying a function or something just to see whether there is any correlation between the in situ data and also the one that you predicted?
S- Can you? Sorry, can you repeat the question? I'm not sure I got what you said.
Yeah, so if you could go to that image in which you compared the Mars 20 data with the yeah, this one. So it looks like there is a shift, and also did you, like, my question is, have you tried applying a function or maybe some sort of polynomial function to the Mars 2020 data to see whether you can fit it in some way or form to the wind data that you predicted.
But it's okay. So I'm not sure I completely get your question, but I don't expect them to be exactly the same anyway, because it's not exactly the same location. It's like 20 kilometers different. I just because I had those data for the same Mars solar longitude, so I was saying that they should have the same seasonality and the same variation. So it's not especially the mean wind speed that should be exactly the same. It's just like they should have kind of the same behavior. But I'm not trying to figure
that's what
like,
it's not about fitting to the same data. Like now, even though there is like a shift, I can see that even the pattern is not quite the same.
yeah, but also but also
Yeah.
Mars 2020 is within a crater, so
Yeah,
yeah,
okay, maybe the
I'm
wall
not too
effects is also playing
I'm
a
not
role in it.
yeah, I'm not too surprised that it's not exactly the same, you know.
Mm-hmm. Okay. Yeah. Thank you anyways, Chloe. Interesting work.
Thank you.
Thank you for the question.
So Matt has a
How about we go
question
to
now. Yeah.
Matt, and then we'll read one from the chat.
Yes.
Oh yeah, thank you, Chloe, for the presentation. It was fantastic. I had first had a comment on the Nili Patera and the Moreau case. So those are just the main distinction is Nili Patera's the dunes are within the caldera, and there's a pretty impressive speed up effect that I think makes it kind of a special place, and it's part of the reason that Simone Silvestre was able to see ripple movement after just a few months of data tracking in the very beginning of the HiRISE mission. And Moreau Patera is kind of out on the flank of a volcano, and so it's further towards the equator. So just a comment is those boundary condition contexts clues are part of, I think, what's going on with having slightly different curves, although it's really perihelion and the peak heating of the northern and southern hemisphere that drives a lot of sand transport in terms of its annual seasonality and its curve. But my second comment / question is more, it kind of relates to some work that we just had done in GRL, where we looked at the seasonal ripple changes of a reversing dune field. And so that's on the edge of a Hellas basin. So like Nili Patera, there's extreme topography, and you've got this waning of the winds with katabatic and anabatic slope winds occurring. And so how do you think about, here we're trying to parse these long dune movements and then the seasonal movements that might be months, but then in reality, we know that the winds go downhill at night and uphill and in the day in some cases. And how do you parse that diurnal cycle of the winds in your approach?
I'm not. I'm taking the average here, so it would be like an average of all of those effects. But yeah, I don't know how I could just have the daily resolution to do that. So yeah, I think I'm just having like the average of all these effects here included here.
Yeah, for sure. So just an opportunity to take a look at the mesoscale modeling simulations that can give you a little bit of a snapshot of for what's happening, although those are topography limited and it's really hard to get those in a particular place, but they're certainly out there. But yeah, thanks again for the great work.
Thank you for your thoughts on that. Very interesting.
I can read a question from the chat, Chloe. Thank you for the great talk. This is from the USGS at GCMRC. We are wondering if your model for Mars accounts for differences in atmospheric composition between Earth and Mars.
Oh yeah. So I guess maybe he means the transport load. So yes, I am adapting the parameters to Martian conditions. Yes. I hope that was the question.
Yes. Thank you, Chloe. Any other question? Oh, go ahead, Philippe.
Yes, I have a question. So, but if someone else has a question, I can wait a bit. But we have the time, so I can ask my question. So why do you? I didn't understand why you need to use this wind distribution, especially because you were just saying that replying to Matt's question that in fact what you describe is the average flow, right? So why then do you need this Weibull distribution, whatever? So and why not just one value, which is the average wind that you try to infer from the data? Why this distribution?
So you mean here, why am I not just using a mean wind speed?
Yes.
Because just because like so if I use my if I use just a wait. Because like the transport flow, if you use the mean wind speed, it will not necessarily give you the mean sand flux. Or maybe I'm misunderstanding the question, but like the sand flux of the mean wind speed will not give you the mean.
Yes, it's a kind of nonlinear relationship between the flux and the wind velocity.
So yes. So I think I do need the distribution. And then I come back to the mean. Don't you agree?
Yeah, so
I'm not
so you adjust the mean flux, in fact, right? And then from which you deduce the corresponding wind that gives the mean, right? But then I could re-ask my question. So you could fit only, in fact, you fit one value, which is the mean of something. Here, in fact, the mean of the flux. Then this is what you are saying.
Yes.
Okay.
So I could also just use the mean and then try to fit.
I see. Okay. Thank you. Anyone else has questions?
Well, thank you so much again, Chloe. Wonderful presentation. I feel like I have many more questions, but maybe I'll think about them and email you. Let me just wrap up with a couple quick announcements here. My notes. All right, thank you again for a wonderful talk. Just a few reminders here. We encourage everyone to check their ISAR membership. Make sure that you're getting our community updates, such as the June newsletter that just went out. Hopefully you all received that. If not, there's a copy of it on our website. In that newsletter, we announced many updates, but a really important one being the call for the 2026 ISAR Awards nominations. There's many new awards this year, and the award cycle is open until the end of October. We recommend that you go check those out. Please reach out if you have any questions about nominating someone. You can reach us at admin@eolianresearch.com. And with that, thank you again. We hope to see everyone when we continue the series in just a few months, possibly in September, but maybe maybe October. So look for updates on the ISAR website. Chloe, thank you again. It was a wonderful presentation.
Yes, thank you. Thank you, Chloe, and thank you everyone for attending the meeting. Please keep you informed on the ISAR website, but just copy it in the chat and check information there, please. Thank you.